Okay, so the next question that we got on the menu today is asking us, in order to be able to determine her speed, a skydiver carries a tone generator, which is pretty much just a speaker. A friend on the ground at the landing site has equipment for receiving and analyzing sound waves. While the skydiver is falling at terminal speed, that means she is not increasing her speed. That means her speed is constant as she's falling. Her tone generator emits a steady tone of 1480 hertz. You can probably hear that. That might sound like a bass guitar or something like that. Assume the air is calm and that the speed of sound is 343 meters per second, independent of altitude. That's important because the speed of sound actually depends on the air pressure, but we're going to ignore that. And we're just going to use 343 for all across the board. If a friend was on the ground and receives waves at a higher frequency of 3,260 hertz instead of, which is higher than the original that she's doing, what is the skydiver's speed of descent? Answer in meters per second. And if the skydiver was carrying equipment so if the skydiver is emitting sounds and also has a receiver, what would be the frequency of the sound that she receives? This is a very fascinating question. So the most important part of this question here is that we're dealing with the consequence of the Doppler effect, right? Doppler effect. So this is what pretty much the Doppler effect is. Higher frequencies when approaching lower frequencies when I guess the opposite of approaching is leaving. Okay, so let's actually think about this. You ever seen, like, I know in cartoons when people like drop things, it's like it's kind of like that's as the thing is going away from you, as it's falling, it's like, you know, the pitch is going down. So like as it's getting farther away from you, the frequencies are getting lower as they're approaching you. Okay, so that's like kind of maybe how you see the Doppler effect in you know, in like cartoons and stuff. But what's really happening is, like, let's say you have like a dot right here and you're having just regular waves and they're going out at a certain frequency, right? So, you know, this is like your regular wavelength. So as it's approaching you, like this, you know, it makes the wave here, but they kind of get a lot, like the wavelengths get a lot closer together because you're moving in proportion to the wave. Like you set out a sound. If I'm moving with the sound, like it's going to get higher frequencies. So this area is like compression. Leads to higher frequencies. And if you're on the other side, let's put this in a different color. If you're on the blue side here, you can see that like the waves are like spreading out because I'm moving and I'm producing new waves in a different position than the previous. That this kind of going to contribute to the change in the wavelength. So spread, and this leads to lower frequencies. Okay, cool. So let's extract some of our given information and then try to calculate what's going on, because there are some nice Doppler effect equations that can definitely help us come to a conclusion here. Okay, so we have a skydiver terminal. So our velocity is going to be constant, which is nice. And we know that the tone generator, so the F source, I think they use F source, right? Yeah, so I use FE, but we can use F source. This is 1480 hertz. So the F ground, that's going to be, that was given as 3,260. So the V sound was given as 343 meters per second. And we need to now solve for the velocity of the diver. Solve for. Okay, cool. So what we're going to do here is we're going to use our Doppler equation, which looks like this. Doppler equation for approaches, or for approaching objects. Okay, so here's the equation for the Doppler effect with approaching objects. We have the frequency as observed by the observer. So let's call that F ground, because in this case the observer is on the ground. And we know that it's going to be the same as the F source, but the F source needs to be scaled. And the amount that it's scaled by is the sum of the velocity of sound over the velocity of sound minus the velocity of the diver. Now, if we were like perhaps in the airplane above, and this would be plus instead. So when it's approaching, we have negative, or we have a minus in the denominator. If it's something that's getting away from us, it's a positive in the denominator. Okay, so this is, let's isolate, we have to isolate F diver, and that will give us exactly what we need. So first, let's bring the F's to the same side. So we have FG, G for ground, just to make this a little bit shorter to write, and then VSOS, speed of sound, SOS, VSOS minus VD. Okay, then we're going to multiply both sides by the denominator of the right side here. And we can put the reciprocal of FG, FS to the other side. So we're going to have VSOS minus VD is equal to F of S over F of G, VSOS. And now to isolate VD, we will do VSOS minus FS over FG, VSOS. And then we can factor out the VSOS from the right side. So we can have VD is equal to VSOS multiplied by 1 minus FS over FG. Now, we were given all the numbers that we need for this, so how about we just sub them in, and we can calculate the numbers, or the result, for the velocity of the diver. So the VSOS, that was 343 meters per second. Here we have 1 minus, now what was the source? The source was 1480 hertz. So 1480 hertz over 3260 hertz. Okay, now we send that through my calculator and we can see what we get. Cool, so the result that I calculated was VD is equal to 187.28 meters per second. Okay, seems like a reasonable calculation. It seems that the given solution here agrees with us, but this calculation is a little bit wonky, so we gotta watch out for that. And now for what the receiver hears, or what the diver hears, so essentially what is heard at the ground is like directly reflected back up, and you know, now it's a situation where we want to see the Doppler effect again, but on the reflected wave. So the source in this case, so for part 2, the reflected wave. We know that in this case, the source is the ground. So the frequency of the source in this case is, well, it'd be the same as what the ground was hearing originally, which was 3260 hertz. Okay, the velocity of sound, VSOS, is going to be the same, so 343 meters per second. And we know that the person is falling at 187, so V diver is equal to 187.28 meters per second. Now we're going to be pretty much using the same equation as before, because even though the source is like not moving, actually my bad, the source is not moving, it's the observer that's moving. So the more formal equation for the Doppler effect for a stationary source so here's the general equation. It looks as followed. Okay, so we have F observed is equal to the F's of the source times the velocity of sound plus the velocity of the observer and then this is over the VSOS, the speed of sound, minus plus the velocity of the source. Okay. So it's minus for when we're approaching, and plus for when we are, getting farther away from it. But in this case, the source is the ground, and it does not move. Zeroes out. Okay, so essentially we just have to sub in the equation. So the observed we don't really need to do any algebra because it's already organized in the proper way. So we have F observed is equal to Fs for F source and then VSOS plus VD, the diver is the observer in this case, all over the VSOS. And I guess we can do minus 0 because the source is not moving, but we don't really need to write that. And let's sub in our numbers and figure this thing out. Is equal to the source in this case is the reflected signal off of the ground. So it's immediately after it was reflected off the ground, it was 3260 hertz multiplied by the speed of sound, which is or the fraction of 343 meters per second plus 187.28 meters per second, all over 343 meters per second. Okay, now I was sending this to my calculator to figure what this is. 3260 multiplied by the fraction of 343 plus 187.28 all over 343. The result of this I expect to be higher than its original, and in this case we found it to be 5040 hertz. Just about. Like, we're rounding a little bit here, but yeah, we're going to hear a much higher frequency, and it seems that the calculation here agrees with us. So the above solution is it's mostly good. So the fraction fraction to find velocity diver is wrong. The shown should be flipped because the calculation as is would lead to a negative result. Cool.